Hey guys, welcome back to my channel. Today we're going to talk about the OSPF protocol, which is also called as Open Shortest Path First. So this is one of the interior gateway protocols. It's a type of a routing protocol. When I say interior gateway protocol, that means it works within an autonomous system. As we discussed in BGP, like every organization will be assigned an autonomous system, and this is a protocol which generally runs within an autonomous system. Okay, so it's a link state routing protocol that uses the shortest path first, or also called as Dijkstra's algorithm, to calculate the best route. Okay, the link state basically means that it considers the path whichever is shortest based on the cost of the link. Okay, and we'll see how the Dijkstra's algorithm works and how it calculates the path and everything. Okay, so in OSPF as well, right, we have routers which is running the OSPF protocol, and they have to establish neighbor relationships before exchanging the routes. So they do not exchange the routing tables exactly, but they exchange the information about the network topology. So each OSPF router knows how the network's topology looks like. Okay, they have a map of the network, which is called as link state database. Okay, so whenever I have a router which is configured as OSPF, that particular router will know how the topology will look like. Okay, and they will have all that information of all the networks that it can reach in its link state database. Okay, and based on this information in the database, the OSPF will then run the Dijkstra's algorithm to calculate the best routes, and those particular routes will be added into the routing table. Because each router knows the entire topology of a network, the chance of a routing loop to occur is minimal. Okay, so let's first see in this example over here, right? Let's say I have two routers over here. Okay, let's call them R1 and R2. Okay, so let me just talk about two topologies, what generally is used, okay, in routing sense. Okay, so this one would be part of 10.1.1.1/24, and this interface will also be part of the same network, right? And this network is what? 10.1.1.0/24 network, correct? So OSPF is running between these two links, right? So what happens is, as a configuration on the router, what I'll say is configure OSPF. Okay, I'll have to configure the OSPF with a particular area ID. Okay, area is basically a number which I'm assigning to a set of routers. Okay, so all these routers in that particular area will have this area ID, and these routers will only form neighborships with those routers in that area. I'll explain you more about like how this area resolves certain problems. But for now, just to know as a configuration point of view, that there is a certain number, okay, it's just called as area, which is generally like an IP or a number like 0.0.0.0, or you can just give it as 0. Okay, and the R1 and R2 will have an interface called, let's see, this is EAT1 and this is EAT2. So I'll say that on R1, configure the area ID as 000, configure a router ID which could be my loopback address. Okay, and say that EAT1 is part of this OSPF interface. Okay, so EAT1 interface is part of OSPF. So now that I know that EAT1 is part of the OSPF interface on R1, and on R2 also I'll have a similar configuration, and area ID should be the same for them to form a neighborship. Okay, which will be again 0 on R2. Okay, and R2 also will have EAT1 as a part of that OSPF configuration. Okay, which is, sorry, EAT2 on R2. Okay, so now these two interfaces, EAT1 and EAT2, will be able to form OSPF neighborship. Make sense? So this is called point to point. Okay, it's like EAT1 and EAT2 are basically point to point interfaces because they're directly connected interfaces, and this has the same subnet, right? Same network interface, 10.1.1.0/24. Okay, now there is also a possibility that I can have a configuration or a network topology where I have multiple routers and all these routers are connected via a switch to each other, in that case all of them would be in the same network. Okay, let's see. And then I have a switch A. Okay, let's call this switch A, and then I have another 3 routers. Okay, this is connected like this. Okay, all of them can be a part of 10.1.10/24 network, right? Where this could be dot 1, this could be dot 2, this could be dot 3, dot 4, dot 5, and dot 6. Okay, so in this case, right, do you think it's important to form neighborship between all these routers? So one should dot 1 should form a neighborship with dot 2, with dot 3, with dot 4, with dot 5, with dot 6? Not necessary. What happens if we form neighborship with all the devices? Basically, if we try to form a full mesh topology over here, the number of updates that will go out will be a lot, right? And each router will have to maintain all this information in the routing table. Now we have only 6 routers in this case, but this can scale up very quickly. Say if we have 50 or 100 routers, then right, each router will need to have so many entries in the routing table, and so many updates will keep going out when a new route is added or a new network is added. Okay, so that's why OSPF also has this concept of selecting a designated router, which is called as DR. Okay, let's say this is a DR, and I can also have a BDR, backup designated router. Okay, so this is chosen based on a certain priority which you can give in the configuration. Okay, by default the priority is 1. Now let's say I'll configure this priority as 10 and configure this priority as 5, and everything else is 1. Okay, so now my dot 1 router will be my DR. So all the routers will form a neighborship with only this particular router, with the one with the priority 10. Okay, so dot 4 will not form a neighborship between these two. No, these two will not form. The neighborship will only be formed over here, between here, and between here. Okay, so this is based on the priority. Let's say if everyone has the same priority, then it goes to a tiebreaker. Then the lowest router ID will be chosen as a DR. Okay, designated router, and there's a backup DR if the DR goes down. So all the updates will be sent to the DR, and DR will then again share all the information about the neighbors, networks, and everything with the other devices. Okay, so now we'll see like how this neighborship is formed, what kind of messages are sent, and what are the different types of messages that are used in OSPF. Okay, but yeah, in this kind of topology we can choose a DR, where DR will form a full neighborship with all the other routers. So you don't have to necessarily form a full mesh topology, because there are issues with full mesh topology when we talk about scale. Okay, so let's see. Okay, let's take a simple example of again R1 and R2. Okay, this is configured with 10.1.1/24, and this is 10.1.1.2/24. Okay, this interface is configured with 11.1.1.0/24 network, and this is configured with 13.1.1.0/24 network. Okay, so now this is router R1 and this is router R2. Okay, makes sense. So once I do an OSPF configuration on R1 and R2, and I'll say that let's say this is interface 1 and this is interface 2. Interface 1 of R1 is part of OSPF and interface R2 is part of OSPF. Both belong to area 0. Both have their router ID configured and everything. Okay, then what happens is R1 needs to form OSPF membership with R2, right? So there are different states. Okay, the first state will be once the configuration is done, they'll automatically be in down state. Okay, both the devices will be in down state. Okay, then over here also we use the concept of hello packets, where OSPF neighbors are dynamically discovered by sending hello packets from each OSPF enabled interface on a router. Okay, now hello packets are always sent with multicast IP address. When they are sent to a point-to-point link, multicast IP address is basically 224.0.0.5. If in case you want to talk to the DR, if I have a topology where I have a designated router, then it will be sent to 224.0.0.6. Okay. Now it will be sent to a multicast address. So basically, hello packet is sent out. Okay, with the router ID. Okay, but neighbor ID over here will not be there. Nothing will be there. Okay. So once R2 receives this particular hello packet, R2 will move to what state? R2 will move to init state. Okay. Now what R2 will do? R2 will basically send a reply, okay, our own hello message with its own router ID, okay, and it also knows the router ID of R1 since it already received a hello from it, right? So it will also send the neighbor ID, correct? And once it does neighbor ID, then R1 will again respond with router ID and neighbor ID. Okay, once it responds with router and the neighbor ID, what will happen? Both the devices will move to the next state, which is called as two-way state. Okay, two-way state is where both of them will start communicating with each other now. Okay, so now the concept of hello packet is done. Hello packets are exchanged. Hello packets will basically exchange all the information about what OSPF versions they are using, what is the router ID, what is the area ID, what is the message authentication type they are using, and some other flags will be set. All this information will be exchanged in the hello packet, and once they agree to it, then they go into the two-way state, and then once they go into the two-way state, they'll start with the exchange start state. Okay, so that is basically, okay, let me show you over here, X start. It's called as X start state. Okay, in this state, basically what happens is both the routers will start exchanging a link state database. Okay, they'll start exchanging link state information. They will choose, one device will become a master and the other will become slave in order to have the control over the sequence number, where the master will first send all the information and request for all the information, then the slave will send all the information and request for all the information. Okay, so X start state, and then it moves to exchange state. Okay, exchange state is when you receive the database descriptor. Okay, exchange state is when you get the database descriptor messages. So these messages will basically have LSAs in their headers. Okay, LSA is basically a type of a packet. Okay, it's called link state agreement headers. Okay, link state agreement headers will basically consist of information about all the networks they have. Okay, so let's say what all networks does R1 has. R1 has 10.1.1.0/24 network. Okay, one more LSA will be of 13.1.1.0/24 network. Okay, correct. So this is the information that will be that R1 has. Okay, so R1 will send this information to R2. Okay, now R2 has this is basically called as database descriptor, DBD. Now using this, okay, R2 will check its link state database. Now what does R2 have? R2 has 10.1.1.0/24 network. It also has 11.1.1.0/24 network. Correct? Okay, this is what R2 has. Okay, now R2 will see that it does not have the 13.1.1.0/24 network, right? So what R2 will do is, now during exchange state, the database descriptor is done. Then they will move to a state called loading state, where R2 has checked that it does not have 13.1.1.0/24 network. So we'll okay, sorry, R1 was the master, right? R1 will first check that 11.1.1.0 is not there. Okay, so R1 will first request to R2 for 11.1.1.0/24 network. Okay, so that is called as LSR, link state request is sent. Okay, then R2 will send an update with the network of 11.1.1.0/24 link state update. Then R1 will send R2 link state acknowledgement saying that, okay, I have received this information, and now in my link state database I basically have 10 network, I have 11 network, and I have 13 network. Okay, this is my link state database, LSDB. Okay, now same thing R2 will do. R2 will check its database descriptor. It will see that it does not have 13 network. It will send a request LSR. It will get an update from the R1, then R2 will acknowledge it, and R2 will also have again same 10.10/24 network, 11.110/24 network, and also it will have 13.1.1.0/24 network. Okay, now both these routers basically have the same LSDB. So all these routers which are part of the OSPF area, okay, will have the same looking LSDB. Okay, so basically R1 will know exactly what all networks it can reach to. It will have a total view of the entire topology of that particular area. Okay, and remember these updates will not cross its area. Okay, it will not go out and update the routers in the other area. It will be always confined within that particular area. Okay, so these are the different types of states we have in the OSPF, where we have the database descriptor, which will send us the link state advertisements, LSAs, and based on what we do not have, we will request using the LSRs, and we'll get the update from the neighbor, and we'll form a LSDB, which will look the same on all the routers which are part of the OSPF and which are part of the same area. So OSPF uses the concept of these areas where we logically group all the contiguous networks and routers in one particular area. All the routers in the same area have the same topology table, they have the same LSDB, and they do not know about the routers in the other areas. The main benefits of creating areas is that the size of the topology is reduced, and the routing table size is reduced, so the amount of time required to process or run the Dijkstra's algorithm is also reduced, and the routing updates are also reduced because the number of LSAs exchanged are less. So we'll see in the next video how it also reduces the how loops are avoided using the areas. And we'll talk about the different types of LSAs we have. We'll talk about the different areas and how the communication happens between different areas, how the route exchange happens between different areas. So I hope the states, different types of states, the different topologies we talked about, the point to point, and having a switch and all the routers connected to that by electing a DR and BDR, how the OSPF works. Um, I hope it all made sense. I'll share a link with you guys. Please go through it and let me know if you have any questions. Uh, Please like, share, and subscribe. Thank you, guys.